So, hello, you can hear me, I guess. I'm Sandra Maier. I'm a PhD student at the NIOZ in the Netherlands, and I would like to talk today about the resource utilization and storage in cold water coral reefs. So, those reefs are occurring in the deep sea, most often between 200 and 800 meters water depth. They are formed by corals, as the name implies, and those support a very high biodiversity. Especially if you look to the left picture, because this is what you normally find at a similar depth. It has been termed a deep sea desert because it looks like this. And it is a desert because food in these areas is usually very limiting. But then the question arises, of course, how on the other hand side can we have those reefs at a similar depth? We know today that cold water coral reefs are fueled by organic matter which is produced in the sunlit surface ocean. And this organic matter has to sink down to the seafloor, but while sinking, a lot of it is already degraded in the water column. There is hydrographic mechanisms like downwelling, which can greatly increase the organic matter supply, but those mechanisms, they are on and active only for a couple of days, and then due to changes in the water column, they can turn off again. And on top of that, in the areas where cold water corals occur, there's usually a very pronounced seasonality. And altogether, this creates something we call feast-famine environment. Feast conditions with a lot of food coming in for a short time, and then for the rest of the time, famine conditions with very little to no food coming into the system. So in a first study, we looked at Haulophilia pertusa, which is the most common cold water coral species, reef-forming cold water coral species in the world, how these corals are dealing with those feast-famine conditions. So in the laboratory, we simulated a feast-famine sequence. We gave the corals a very big food pulse of algal material for 3 days. And for the following 4 weeks, we starved them, so we didn't give them any further food. And the trick of the study was that we really wanted to follow the food peak. So what are the corals doing with it? What do they store it? Do they metabolize it? How do they use it? And for that, we artificially enriched the algae in 13C, using that as a tracer. If you don't know, 13C is the natural, stable, heavy form of isotopic form of carbon, and it is normally very rare in nature. So if we enrich it, it's a tracer material. So we followed this tracer over the whole experiment into the metabolic products of the corals and into their tissue and storage molecules. What we found is something I plotted here. On the y-axis, you can see the amount of carbon that the corals expend for their metabolic processes over the whole experimental time, over the weeks after feeding. And right after having this feast feeding conditions, the corals seem to have a growth phase. So during this phase, we found that they invest carbon into new biomass, they build storage and structural molecules, and the energy they need for that is gained by the enhanced respiration of the food carbon, which you see in the dark gray bar. Also, they seem to lose quite a bit of material as particulate and dissolved organic carbon. After this growth phase, they enter a famine mode. During these 4 weeks, we found that the corals depleted already 50% of the material that they stored from the food peak, which is quite a lot. So that would indicate that from the food pulse we gave them, they would only be able to live off for 8 weeks. So what we wanted to do now is to move a bit away from the corals, which are building the reef, to the organisms that are actually associated with the reef. And we picked 2 species, the bivalve, Acesta excavata, and a sponge, Geodia barretti, who are very common in Norwegian cold water coral reefs. And we wanted to find out if those reef organisms can maybe use alternative food sources, like a bit independent from the surface production. So So the alternative food sources could, for example, be bacteria or dissolved organic matter. Dissolved organic matter, for example, produced by the corals, as we just saw. And what we did, we also offered them bacteria and DOM, dissolved organic matter, and we wanted to find out if they can metabolize those substrates. So if they respire it, they metabolize it. On the y-axis, you see the respiration of this food, and on the x-axis, the different food sources and organisms. And what we found is, yes, indeed, both of those organisms are able to use both bacteria and also dissolved organic matter, which is quite a new finding, especially for the bivalves. So to sum this up a bit, what's actually the question? Well, my question for my PhD is if the storage and recycling is more important or the organic matter from the surface. Thanks.